Imagine being handed a message from a machine you launched 47 years ago, a machine no larger than a small car, traveling through a void so vast and so cold that the very concept of distance begins to lose its meaning. Imagine that this machine, against all odds, is still alive, still transmitting, still measuring, still reaching back across billions of kilometers of emptiness to tell you what it has found. And what it has found is something no one fully expected. Not emptiness, not silence, but a roiling, turbulent, electromagnetically charged boundary, a wall between the kingdom of our sun and the ancient crushing darkness of interstellar space. A boundary that hisses with plasma waves, that floods incoming spacecraft with cosmic radiation, that marks the edge of everything our star has ever touched. This is the story of what Voyager detected at the edge of our solar system, and it begins not with a quiet scientific observation, but with a moment of rupture, the moment a human-made object crossed a threshold that had never been crossed before, and discovered that the universe beyond our sun is nothing like the universe within it. If you love deep space deep dives, you can subscribe. It helps more than you think. To understand what Voyager found, you first have to understand what Voyager is and why it was sent on a journey that was never truly expected to end. The late 1970s were a period of extraordinary ambition in space exploration. NASA had already sent humans to the moon. The Viking landers had touched down on Mars. But the outer solar system, the realm of Jupiter, Saturn, Uranus, and Neptune, remained almost entirely unknown. We had no spacecraft that had visited these worlds up close. We had no measurements of the magnetic fields, the radiation belts, the atmospheric chemistry of these giant planets. They were blurry disks in telescopes, spectacular in their own right, but fundamentally mysterious. And then, in the early 1960s, a graduate student at the California Institute of Technology named Gary Flandro made a calculation that would quietly change the history of space exploration. Working on trajectory optimization problems for NASA, Flandro noticed something remarkable. In the late 1970s, the four giant outer planets, Jupiter, Saturn, Uranus, and Neptune, would be arranged in a configuration that occurs only once every 176 years. They would be positioned in a rough arc across one side of the solar system, in an alignment that would allow a spacecraft launched from Earth to use the gravitational field of each planet in sequence as a kind of cosmic slingshot, gaining speed from each encounter and being flung toward the next destination without expending any additional propellant. This trajectory, which became known as the Grand Tour, it was an opportunity that NASA could not afford to miss. What emerged from this opportunity was the Voyager program. Two nearly identical spacecraft, Voyager 1 and Voyager 2, were constructed at the Jet Propulsion Laboratory in Pasadena, California, and prepared for a journey that would take them first through the outer planets, and then, inevitably, out of the solar system entirely. Each spacecraft weighed roughly 722 kilograms. Each carried a suite of scientific instruments designed to measure magnetic fields, charged particles, plasma waves, and the properties of every environment it would pass through. Each carried a gold-plated phonograph record, the famous Golden Record, etched with sounds and images of Earth, a message in a bottle addressed to the universe, launched on the off chance that something out there might someday find it. Voyager 2 launched first on August 20th, 1977. See Voyager 1 followed 16 days later on September 5th, 1977. Despite the numbering, Voyager 1 was on a faster trajectory and would reach the outer planets first. This was not an accident, but a deliberate design choice. The two spacecraft were sent on different paths to maximize the science return, visiting different moons and exploring different regions of each planetary system. The journey through the inner solar system was relatively brief. Within 2 years, both spacecraft had crossed the asteroid belt and were approaching Jupiter, the largest planet in the solar system. What they found there was staggering. Jupiter is not merely a large version of Earth, it is a fundamentally different kind of world. A planet so massive that its gravitational field shapes the orbits of objects throughout the solar system. A world with a magnetic field so powerful that it extends millions of kilometers into space and creates a radiation environment that would kill an unshielded human in minutes. Voyager's instruments detected this magnetic field from enormous distances, and as the spacecraft approached, they began picking up radio emissions from the Jovian magnetosphere, a complex and dynamic system of charged particles spiraling along magnetic field lines and emitting electromagnetic radiation across a broad spectrum. But it was the visual and in situ observations that captured the world's imagination. The cameras on Voyager 1 revealed Jupiter's cloud bands in unprecedented detail, vast rivers of gas, thousands of kilometers wide, moving in opposite directions at the boundaries where different atmospheric bands met. They revealed the Great Red Spot as a genuinely enormous storm system, a high-pressure anticyclone large enough to swallow multiple Earths, with winds exceeding 400 kilometers per hour. They revealed the 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, as individual, complex worlds in their own right. Io was found to be the most volcanically active body in the solar system, with plumes of sulfur dioxide erupting hundreds of kilometers above its surface. Europa showed a cracked, icy surface that hinted at a liquid water ocean beneath, a discovery that would, decades later, make it one of the most promising candidates in the solar system for the existence of extraterrestrial life. The gravitational slingshot from Jupiter accelerated the spacecraft significantly. Voyager 1 picked up approximately 10 kilometers per second of velocity from its Jupiter encounter, setting it on a faster trajectory towards Saturn. Voyager 2 received a similar boost, though on a different path that would eventually allow it to continue on to Uranus and Neptune. Saturn, the second destination, proved to be equally revelatory. The rings, which had been observed from Earth for centuries, were revealed by Voyager to be vastly more complex than anyone had imagined. Not solid disks, but intricate dynamic structures composed of billions of individual particles of ice and rock, ranging in size from grains of sand to boulders the size of houses. The rings were divided into hundreds of distinct ringlets, some of them twisted into braided structures by the gravitational influence of small shepherd moons orbiting at the ring edges. The Cassini division, the large gap visible in the rings from Earth, turned out to contain not empty space but a series of fainter rings of its own. Saturn's largest moon, Titan, received particular attention. Voyager 1's trajectory was adjusted specifically to allow a close flyby of Titan, because pre-mission observations had suggested that it possessed a substantial atmosphere, the only moon in the solar system known to do so. The encounter confirmed this and exceeded expectations. Titan's atmosphere was found to be denser than Earth's, composed primarily of nitrogen, with significant amounts of methane and a complex mixture of organic compounds produced by photochemical reactions. The dense orange haze that enveloped Titan prevented the cameras from seeing the surface directly, but the atmospheric data alone was extraordinary. Here was a world with weather, with a hydrological cycle driven not by water but by methane, with rain and rivers and possibly even seas of liquid hydrocarbons on its surface. In choosing to fly close to Titan, mission planners had sacrificed the possibility of continuing on to Uranus and Neptune. The gravitational geometry of the close Titan encounter bent Voyager 1's path out of the plane of the solar system, ensuring that it would eventually exit the solar system above the ecliptic rather than continuing along the paths of the outer planets. Voyager 2, on its different trajectory, was free to continue the Grand Tour. After its own Saturn encounter, it went on to become the only spacecraft in history to visit Uranus and Neptune. At Uranus, it found a world tilted on its side, rotating with its poles pointing almost directly at the Sun, with a pale blue-green atmosphere, a complex system of rings far darker than Saturn's, and a collection of small, geologically diverse moons, including Miranda, which showed evidence of some of the most dramatic terrain in the solar system, with cliffs nearly 20 kilometers tall. At Neptune, Voyager 2's final planetary encounter, it discovered a dynamic world with the strongest winds in the solar system, a massive storm system called the Great Dark Spot, analogous to Jupiter's Great Red Spot, and perhaps most dramatically, The moon, Triton, a world orbiting Neptune in the wrong direction, clearly a captured Kuiper Belt object with geysers of nitrogen gas erupting from its frozen surface. By the time Voyager 2 completed its Neptune encounter in August 1989, both spacecraft had already been traveling for 12 years. They had collectively rewritten the planetary science textbooks, providing humanity's first detailed views of 4 giant worlds and dozens of their moons. They had demonstrated that the outer solar system was not a cold, dead place, but a region of extraordinary geological and atmospheric activity. But, in a very real sense, their most important discoveries still lay ahead, because now, having completed their work among the planets, the Voyagers were heading outward into territory that had never been measured before. They were heading for the edge. To understand what Voyager encountered at the edge of the solar system, so you have to understand what the solar system's edge actually is. This is not as simple as it might seem. The solar system does not end at the orbit of Neptune, though Neptune's orbit, at roughly 30 astronomical units from the Sun, where 1 astronomical unit is the average distance from the Earth to the Sun, is the outermost region of the classical planetary system. Beyond Neptune lies the Kuiper Belt, a broad disk of icy bodies extending from about 30 to 50 astronomical units, the source of short-period comets and the home of dwarf planets like Pluto, Eris, Makemake, and Haumea. Beyond the Kuiper Belt lies the scattered disk, a more dispersed population of icy objects on highly elliptical orbits. And beyond even that, at distances of thousands to tens of thousands of astronomical units, lies the Oort cloud, a vast spherical shell of cometary nuclei that represents the gravitational limit of the Sun's dominance over small bodies. But none of these structures represents the true boundary of the Sun's direct physical influence. That boundary is defined not by gravity and solid bodies, but by the solar wind. And the solar wind is what the Voyager spacecraft spent decades measuring their way through. The solar wind is one of the most fundamental phenomena in our solar system, yet it is invisible and utterly imperceptible to our unaided senses. It is a continuous outflow of charged particles, primarily protons and electrons, with a smaller component of helium nuclei, streaming outward from the Sun's corona in all directions at speeds typically ranging from 400 to 800 kilometers per second. The corona, the Sun's outermost atmospheric layer, is heated by processes that are still not entirely understood to temperatures of several million degrees Kelvin, far hotter than the solar surface itself, which sits at a comparatively cool 5,778 degrees Kelvin. At these extreme coronal temperatures, the thermal energy of the particles is sufficient to overcome the Sun's gravitational pull, and a continuous stream of plasma boils off into space, filling the entire solar system with this tenuous but relentless outflow. The solar wind carries with it the Sun's magnetic field. Because the Sun rotates on its axis approximately once every 25 days, and because the solar wind carries the field outward as it flows, the interplanetary magnetic field does not radiate straight outward from the Sun like the spokes of a wheel. Instead, it takes on a spiral structure, winding outward through the solar system in the shape of an Archimedean spiral, a pattern that physicists call the Parker spiral, named after Eugene Parker, who first predicted its existence in 1958. The interplanetary magnetic field permeates the entire inner and outer solar system, threading through the space between the planets and extending outward to enormous distances. As the solar wind travels outward, it gradually loses energy and density. The density falls off as the square of the distance from the Sun. At twice the distance, the same number of particles must fill 4 times the volume. By the time the solar wind reaches the orbit of Saturn, it is already extremely tenuous by any terrestrial standard, containing only a few particles per cubic centimeter. By the orbit of Neptune, it is more tenuous still, but it is still moving outward, still carrying the Sun's magnetic field, still defining the space it flows through as fundamentally solar rather than interstellar. Eventually, however, the outward flowing solar wind must meet resistance. In interstellar space, There is not a true vacuum. The space between the stars is filled with the interstellar medium, a diffuse mixture of gas and dust with its own density, its own temperature, and its own magnetic field. The interstellar medium pushes back against the solar wind, and at a certain distance from the Sun, the pressure of the solar wind decreases to the point where it can no longer push the interstellar medium out of the way. At that point, something remarkable happens. The first boundary, moving outward from the Sun, is called the termination shock. This is the point at which the solar wind transitions from supersonic to subsonic flow, where the outward moving plasma abruptly slows down, heats up, and becomes denser as it is forced to decelerate by the mounting pressure of the interstellar medium. The termination shock is not a sharp, thin surface, but a complex dynamic region that ripples and fluctuates with changes in solar activity. When solar flares and coronal mass ejections send pulses of denser, faster solar wind outward, the termination shock expands. During periods of low solar activity, it contracts, but on average, it lies at roughly 75 to 100 astronomical units from the Sun. Beyond the termination shock lies a region called the heliosheath, the zone of shocked, slowed solar wind that extends from the termination shock outward to the heliopause. In the heliosheath, the solar wind is no longer supersonic. It has been heated and compressed by the shock, and it meanders outward in a more turbulent, complex fashion, being pushed and deflected by the interstellar medium. The heliosheath is thick, spanning tens of astronomical units, and it is, in many ways, the most dynamic and unexpected region that the Voyager spacecraft encountered. The outermost boundary, the true edge of the Sun's domain, is the heliopause. This is the surface at which the solar wind's pressure and the interstellar medium's pressure are in equilibrium, where the two meet and neither can advance. At the heliopause, the solar wind essentially stops. The Sun's particles do not cross this boundary to any significant degree. The magnetic field carried outward by the solar wind is deflected. Beyond this line, in interstellar space, the properties of the plasma, the magnetic field, and the particle populations are fundamentally different from those within the heliosphere. This is the true edge of the Sun's influence, and this is what the Voyager spacecraft were, slowly and incrementally approaching. The first spacecraft to reach the termination shock was Voyager 1, but the exact moment of crossing was not immediately obvious. The termination shock is not a fixed location, and its position fluctuates substantially over time. The instruments on Voyager 1 had been detecting changes in the solar wind for years as the spacecraft moved outward, watching the plasma slow and the magnetic field weaken. Scientists at JPL and at universities around the world who were monitoring the data had been making predictions for years about when the termination shock crossing would occur. What actually happened was more complex and more interesting than the models had predicted. In late 2003 and early 2004, as Voyager 1 was approaching approximately 85 astronomical units from the Sun, the particle instruments began detecting something anomalous. The flux of energetic particles accelerated to high energies in the termination shock region, began increasing dramatically. This was a sign that the spacecraft was near the termination shock, because the shock is a powerful particle accelerator and energetic particles diffuse away from it in all directions, including back toward the Sun. If you are approaching the termination shock, you will begin to see more and more of these energetic particles as you get closer. But then something strange happened. In late 2003, before any definitive crossing had been observed, the levels of energetic particles dropped back down, and the solar wind speed, which had been expected to drop sharply at the termination shock, remained relatively high. The simplest interpretation was that the termination shock had moved, that a pulse of faster solar wind from a solar event had pushed the termination shock outward, away from the spacecraft, and the spacecraft had not actually crossed it yet. Then, in December 2004, the crossing occurred, or rather, the crossings occurred because the termination shock turned out to be not a single clean boundary, but a dynamic, fluctuating structure that the spacecraft crossed and recrossed multiple times as it moved through, and the shock oscillated in position. The particle flux data, the magnetic field data, and the plasma wave data all showed the characteristic signatures of the crossing. The solar wind speed dropped sharply, the magnetic field strength increased, the density of the plasma rose. Voyager 1 had crossed into the heliosheath. Voyager 2's termination shock crossing came later, in August 2007, at a distance of about 83.7 astronomical units from the Sun. The fact that Voyager 2 crossed the termination shock at a slightly smaller distance than Voyager 1, which had crossed at about 94 astronomical units, was itself scientifically significant. The two spacecraft were moving in different directions. Voyager 1 was heading northward out of the ecliptic plane, while Voyager 2 was heading southward. The fact that the shock was at different distances in the two directions suggested that the heliosphere is not perfectly spherical, that it is asymmetric, likely because the interstellar medium is not flowing uniformly from all directions, but is moving relative to the Sun, distorting the heliosphere into an elongated, comet-like shape with a compressed front end and a stretched-out tail. Crucially, Voyager 2 had a functional plasma science instrument that Voyager 1 lacked. Voyager 1's plasma instrument had failed years earlier. This meant that for the first time, as Voyager 2 crossed the termination shock, scientists had direct measurements of the solar wind plasma's velocity, density, and temperature. These measurements confirmed the theoretical predictions in the broad outline, but also revealed unexpected details. The solar wind speed dropped from around 400 kilometers per second to less than 150 kilometers per second, almost instantaneously at the shock crossing. The plasma temperature rose dramatically by a factor of roughly 20, from about 50,000 Kelvin to nearly 1,000,000 Kelvin. The plasma had been heated by the shock, but there was a problem. The models had predicted that the termination shock would heat the protons in the solar wind to very high temperatures, high enough to account for most of the energy in the slowing solar wind. But the Voyager 2 data showed that the protons had not been heated as much as expected. Something else had absorbed the energy. Later analysis suggested that the energy was going into the accelerated ion population, the energetic particles, predominantly heavier ions, that were being accelerated to very high energies at the shock. This was an unexpected result with significant implications for the physics of shocks throughout the universe, because the termination shock is in many ways a model system for understanding how shocks in other astrophysical contexts, supernova remnants, for instance, accelerate particles. Now both spacecraft were in the heliosheath, the strange twilight zone between the solar kingdom and the interstellar realm, and what they found there confounded nearly every model that had been constructed to describe it. The heliosheath was expected to be a relatively simple region, a zone of subsonic, turbulent solar wind being gradually decelerated and diverted as it approached the heliopause. The pre-mission models had generally predicted that the heliosheath would be relatively thin, perhaps 10 to 20 astronomical units across, and that the solar wind would maintain a more or less outward flow as it moved through it. What the Voyager spacecraft found was far more complex. The heliosheath turned out to be much thicker than anticipated, roughly 25 to 35 astronomical units, based on where the heliopause crossings ultimately occurred, and within it, the plasma was behaving in highly unexpected ways. One of the most puzzling phenomena detected in the heliosheath was what appeared to be a dramatic slowing, even reversal, of the radial solar wind flow. In 2010, Voyager 1's instruments detected something that the mission team called a stagnation region. At approximately 113 astronomical units from the Sun, the outward flow of the solar wind appeared to drop to nearly zero. The plasma was not flowing outward. It was not flowing inward. It was, in some sense, barely flowing at all. This was deeply unexpected. Where was the solar wind going? Part of the answer involves what happens to the solar wind in the heliosheath when it loses its protons. Energetic neutral atoms, formed when the hot protons in the heliosheath exchange charges with cold interstellar hydrogen atoms that have penetrated into the heliosphere, carry energy out of the heliosheath without being confined by the magnetic field. This process transfers energy out of the solar wind proton population, you're cooling and decelerating the plasma in ways that were difficult to model accurately before Voyager's measurements. The stagnation region appeared to be a zone where this process had been so effective that the solar wind had essentially lost most of its outward momentum. The heliosheath also exhibited a complex magnetic field structure that surprised the modelers. Because the interstellar medium is flowing relative to the Sun, the heliopause is not simply a static spherical shell. The heliosphere has a nose, the part of the heliopause facing into the incoming flow of the interstellar medium, and a tail, the part being pushed away. In the nose region, which both Voyager spacecraft were approaching, the interstellar medium pushes against the heliosphere, compressing it. The magnetic field in the heliosheath in this region was observed to be folded and piled up in complex ways, building up against the heliopause like water piling up in front of a dam. The structure of the heliosheath also presented surprises in its large-scale geometry. Pre-mission models had generally assumed that the heliosphere is roughly symmetric, that the heliopause is more or less spherical, deformed only modestly by the motion of the solar system through the interstellar medium. What the Voyager data began to suggest, and what subsequent remote sensing observations have confirmed, is that the heliosphere is far more asymmetric than those models predicted. The nose of the heliosphere, pointing in the direction of the solar system's motion through the local interstellar cloud, is compressed. The flanks are broader, and the tail, the downstream region, is thought to be elongated into a vast structure, stretching perhaps hundreds of astronomical units behind the Sun. This tail, sometimes called the heliotail, and has been mapped in its gross outlines using energetic neutral atom imaging from spacecraft in the inner solar system, but its full extent and structure remain uncertain. The two Voyager spacecraft, in crossing the heliopause in different directions and at slightly different distances, provided two data points in this three-dimensional geometry. The data confirmed that the nose of the heliosphere is where both spacecraft were heading, the upstream direction, and that the distances to the heliopause in these directions were similar but not identical, reflecting the detailed asymmetries caused by the interstellar magnetic field pressure on the heliosphere. The energetic particle environment in the heliosheath was also dramatically different from anything in the inner solar system. Within the heliosphere, the dominant energetic particle populations are solar energetic particles, particles accelerated by solar flares and coronal mass ejections, and anomalous cosmic rays, which are ions from the interstellar medium that have been ionized and accelerated at the termination shock. Galactic cosmic rays, particles accelerated outside the solar system, see predominantly in supernova remnants and other high-energy astrophysical processes, are present throughout the heliosphere but are partially excluded by the Sun's magnetic field, which acts as a partial shield. The deeper you go into the heliosphere, the fewer galactic cosmic rays you find. In the heliosheath, the balance shifts. The anomalous cosmic ray intensity increases near the termination shock and then varies in complex ways through the heliosheath. The galactic cosmic ray intensity is higher than in the inner solar system, but still somewhat suppressed by the heliospheric magnetic field. And as both Voyager spacecraft move through the heliosheath toward the heliopause, the galactic cosmic ray intensity began a gradual, steady increase, a climb that would accelerate dramatically as they approached the final boundary. The heliopause crossing of Voyager 1 is one of the most precisely documented and scientifically debated events in the history of space exploration. It did not happen in a single moment. It unfolded over months, in a series of measurements that forced the scientists monitoring the data to rethink their definition of what crossing a boundary actually means. In the first half of 2012, as Voyager 1 was at approximately 120 astronomical units from the Sun, the particle instruments began registering dramatic changes. The flux of low-energy ions of solar origin, particles that had been created within the heliosphere and were being carried outward by the solar wind, began a sharp decline. At the same time, the flux of galactic cosmic rays began a steep increase. This was exactly the pattern that would be expected at the heliopause. Inside the heliopause, solar particles dominate. Outside, galactic cosmic rays dominate. But something was wrong, or at least unexpected. The magnetic field direction and strength, which should also change dramatically at the heliopause, did not change in the way the models had predicted. The field strength increased, which was expected. The heliospheric magnetic field piles up against the heliopause, but the field direction, the orientation of the magnetic field lines, remained roughly the same as it had been in the Helios Heath, rather than rotating to align with the expected orientation of the interstellar magnetic field, which was thought to come from a significantly different direction. The scientific community was genuinely uncertain about how to interpret this. Some team members argued that Voyager 1 had crossed the heliopause in late July or early August of 2012, when the solar particle flux dropped dramatically. Others pointed to the lack of magnetic field direction change as evidence that the spacecraft had not yet fully exited the heliosphere. Some proposed novel models in which Voyager 1 had entered a region called the heliocliff, a region of the outermost heliosheath with very unusual properties. The plasma wave instrument provided the key piece of evidence. This instrument measures oscillations in the plasma, waves that travel through the charged particles at specific frequencies that depend on the electron density of the medium. In April 2013, the plasma wave instrument detected a strong burst of electron plasma oscillations. By measuring the frequency of these oscillations, which in a plasma are directly related to the electron density by a simple formula, the team could calculate the density of the electrons surrounding Voyager 1 at that moment. What they found was startling. The electron density was approximately 0.08 electrons per cubic centimeter. This is roughly 40 times higher than the density that had been measured in the outer heliosheath. This density was entirely consistent with theoretical predictions for the density of the interstellar medium just outside the heliopause. Voyager 1 was in interstellar space, or at least, it was surrounded by interstellar plasma. Further analysis of the plasma wave data, combined with the particle data, allowed the team to reconstruct a timeline. It appeared that Voyager 1 had actually crossed the heliopause in late August 2012, when the solar particle flux had experienced its sharpest decline and the galactic cosmic ray flux had made its most dramatic jump. The April 2013 plasma wave event and a similar event in October 2013 were the results of solar outbursts, eruptions of coronal mass ejections from the Sun that had sent pressure waves outward through the heliosheath. These waves had propagated outward and, when they struck the denser interstellar plasma surrounding Voyager 1, had set up the oscillations that the plasma wave instrument detected. The frequency of those oscillations told scientists the density of the plasma, which told them where they were. The official announcement came in September 2013. Voyager 1 had entered interstellar space. It was the first human-made object to do so. At the time of the announcement, it was approximately 19.3 billion kilometers, nearly 130 astronomical units, from the Sun. But the scientific story was not simple, and the debate about the magnetic field direction continued. The puzzle was eventually resolved through a combination of further analysis and a recognition that the interstellar magnetic field direction near the heliopause may be strongly influenced by the draping of interstellar field lines around the heliosphere, a complex interaction that rotates the local field direction to be more similar to the heliospheric field than to the undisturbed interstellar field far from the solar system. The boundary had been crossed, but the boundary itself was far more complex and multi-layered than the pre-mission models had envisioned. The plasma wave oscillations detected by Voyager 1 in the interstellar medium were not merely diagnostic tools. They were, in themselves, extraordinary discoveries. Plasma waves are a fundamental form of energy transport and communication in magnetized plasmas, and the detection of strong, well-defined oscillations in the interstellar plasma near the heliopause revealed something important about the structure of that medium. The plasma wave science instrument on Voyager 1 was designed to detect electric field oscillations in the frequency range of roughly 10 Hz to 56 kHz. Different types of plasma waves occupy different frequency ranges, and the physics of the waves carries information about the density, temperature, and magnetic field of the plasma in which they propagate. In the Helios Heath, the instrument had been detecting various types of wave activity associated with the complex turbulent plasma conditions. but the events detected in April and October 2013 and in subsequent years had a very specific character. They were electron plasma oscillations, also called Langmuir waves, at a frequency that indicated an electron density of roughly 0.08 per cubic centimeter. What caused these oscillations? The answer appears to be shock waves propagating outward from the Sun. When the Sun erupts, ejecting billions of tons of magnetized plasma in a coronal mass ejection, or producing a sudden increase in the solar wind speed, the resulting disturbance propagates outward through the heliosphere as a pressure wave. When this wave crosses the heliopause and enters the denser interstellar medium, the sudden compression of the interstellar plasma can drive oscillations at the electron plasma frequency, essentially setting the interstellar plasma ringing at its natural frequency. Subsequent years of data from Voyager 1's plasma wave instrument have detected multiple such events, each triggered by solar activity that occurred months to years before the observation, the time it takes for the disturbance to travel from the Sun to Voyager's position, which grows further from the Sun with every passing year. These observations have effectively allowed scientists to use Voyager 1 as a remote probe of solar activity, observing the effects of solar eruptions in the interstellar medium long after the eruptions themselves occurred. Perhaps more importantly, the sequential detection of these events at different times, combined with knowledge of when the solar eruptions occurred, has allowed scientists to track the evolution of the plasma density in the interstellar medium as Voyager moves deeper into it. And what they have found is that the electron density, while remaining broadly consistent with the approximately 0.08 per cubic centimeter value measured in 2013, shows significant variation, suggesting that the interstellar medium near the heliopause is not uniform, but structured, with density variations that may reflect the complex interaction between the heliosphere and the interstellar medium. The plasma wave instrument also detected another type of wave activity in the interstellar medium, so-called tsunami waves, which are the term some team members have used informally to describe the large-scale pressure disturbances propagating outward from the Sun. When an unusually powerful solar event occurs, a major coronal mass ejection, or a sequence of such events, the resulting pressure wave can be large enough to measurably compress the interstellar medium at Voyager's location, producing a well-defined wave signature in the plasma oscillation data. These observations confirm that the Sun's influence does not entirely stop at the heliopause. The pressure of solar eruptions can propagate outward into the nearby interstellar medium, now compressing it and creating detectable disturbances. The boundary is not impermeable. It breathes with the rhythm of the Sun's activity cycle. While the plasma wave observations provided some of the most spectacular and direct evidence of Voyager's transition into interstellar space, the cosmic ray data told an equally compelling story, one that unfolded more gradually and revealed fundamental aspects of how our solar system shields itself from the universe. Cosmic rays are not, but despite their name, a form of electromagnetic radiation. They are particles, primarily protons, but also helium nuclei and heavier ions, as well as electrons, that have been accelerated to very high energies by processes elsewhere in the galaxy. The most energetic cosmic rays carry kinetic energies billions of times greater than what can be achieved by the most powerful particle accelerators on Earth. The primary sources of galactic cosmic rays are thought to be the shock waves of supernova remnants, the expanding shells of debris and compressed interstellar medium left behind when massive stars explode. As the remnant shock wave sweeps through the interstellar medium, it can repeatedly accelerate charged particles to very high energies through a process called diffusive shock acceleration, bouncing particles back and forth across the shock front and adding energy with each crossing. These galactic cosmic rays pervade the Milky Way. They fill the interstellar medium with a sea of energetic particles that travel at close to the speed of light, spiraling along magnetic field lines and slowly diffusing through the galaxy. Were it not for the heliosphere, the Earth would be bathed in a much more intense flux of galactic cosmic rays than it actually receives. The heliosphere and particularly the solar wind's outward flow and the associated magnetic field, acts as a shield. Low-energy galactic cosmic rays, those with energies below a few hundred mega-electron-volts per nucleon, are particularly effectively excluded by the heliospheric magnetic field. They can penetrate the outer heliosphere, but they are attenuated and slowed by the opposing outward flow of the solar wind and by the tangled magnetic field structure of the heliosheath. As Voyager 1 moved outward through the heliosheath, its cosmic ray instrument monitored the intensities of particles in various energy ranges. The low-energy galactic cosmic ray intensity increased steadily as the spacecraft moved through the heliosheath, climbing as the shielding provided by the heliospheric magnetic field became thinner. But the truly dramatic change came at the Heliopause crossing. In August 2012, as Voyager 1 crossed the Heliopause, the low-energy galactic cosmic ray intensity jumped by approximately a factor of 2 in a matter of days. This was not a gradual increase. It was a step change, and it was accompanied by the simultaneous disappearance of the anomalous cosmic rays, which are found only within the heliosphere. The particle environment on one side of the Heliopause was radically different from the particle environment on the other side. The transition was as clean and distinct as crossing a physical barrier, which, in a meaningful sense, is exactly what it was. The data from the cosmic ray instrument painted a clear picture. The Heliopause is a genuine boundary in the particle environment of the solar system. Galactic cosmic rays exist at much higher intensities outside the Heliopause than inside, confirming that the heliosphere provides substantial shielding. Anomalous cosmic rays, which are a signature of the termination shock and the heliosheath, disappear at the Heliopause. The interstellar medium beyond the Heliopause has a particle environment that is dominated by galactic cosmic rays and by interstellar pickup ions. Ions formed when neutral interstellar atoms enter the heliosphere and become ionized, then are carried outward and mixed into the solar wind and eventually into the helioheath. For human space exploration, these measurements have direct and sobering implications. Any future interstellar mission, or even a very long-duration mission into the outer heliosphere, would need to contend with a substantially higher cosmic ray dose than missions in the inner solar system. While the Earth's atmosphere and magnetic field provide protection for surface life, astronauts in deep space would be exposed to the full interstellar cosmic ray flux, which is significantly more intense than what they experience in low Earth orbit or even on missions to the Moon. The Voyager data has provided the first direct calibration of what that dose would actually be. The magnetic field measurements made by Voyager 1 and Voyager 2 near and beyond the Heliopause have provided some of the most unexpected and scientifically contentious results of the entire mission. Magnetic fields are in some ways the most fundamental property of the plasma environments that Voyager traverses. They determine how particles move, how energy is transported, and how the different regions of the heliosphere are structured. And the magnetic field data from the Voyager magnetometers has consistently surprised the theoretical community. The pre-mission models of the heliosphere generally predicted that the heliospheric magnetic field, the Parker spiral field carried outward by the solar wind, would be distinctly separated from the interstellar magnetic field at the Heliopause. On the heliospheric side, the field would be dominated by the Sun's magnetic field, carried outward and wound into the spiral pattern. On the interstellar side, the field would reflect the local interstellar magnetic field, which was predicted to come from a direction significantly different from the heliospheric field at the Heliopause, based on pre-mission observations and models. What Voyager 1 found was that the magnetic field direction did not change significantly at the Heliopause. The field on both sides of the boundary was oriented in roughly the same direction, nearly radially outward from the Sun in the ecliptic plane, or more precisely, in the direction of the Parker spiral field at that distance. This was genuinely puzzling. It seemed to imply either that the interstellar magnetic field near the Heliopause had been deflected and aligned with the heliospheric field by the interaction between the two regions, or that the pre-mission predictions about the interstellar field direction were wrong. Subsequent analysis favored the first explanation. The interstellar magnetic field that passes near the heliopause is expected to be draped around the heliosphere by the relative motion of the interstellar medium. Just as the magnetic field carried by the solar wind is shaped by the geometry of the solar system, the interstellar magnetic field is deformed and draped around the heliosphere by the flow of the interstellar medium past it. In the region just outside the heliopause, where Voyager 1 has been traveling, the draped interstellar field may be nearly parallel to the heliospheric field, producing the similarity in direction that was observed. The crossing also provided a rare and precious opportunity to compare conditions on both sides of the heliopause at the same moment in time, something that single spacecraft observations can never fully achieve. Because Voyager 2's instruments were measuring the solar wind, the heliosheath, and then the interstellar medium, in a continuous sequence, the team could directly compare the properties of the plasma on each side of the boundary using the same instruments with the same calibration. This is scientifically invaluable. It means that the differences observed between heliosheath plasma and interstellar plasma cannot be attributed to instrument calibration differences or to different measurement techniques. They are real, physical differences in the two environments. What those differences showed was stark. The solar wind plasma in the heliosheath, even after being slowed and heated at the termination shock, had a fundamentally different character from the interstellar plasma. The heliosheath plasma was cooler and less dense than the interstellar plasma immediately outside the heliopause. Counterintuitive at first, since one might expect the sun's influence to make the inner region hotter, but explicable when one considers that the interstellar plasma in the boundary layer has been compressed and heated by the interaction with the heliosphere. The magnetic field strength increased modestly across the heliopause, and its direction remained relatively similar on both sides, as had been the case for Voyager 1. One of the most significant aspects of Voyager 2's heliopause crossing was the direct measurement of the boundary layer, a thin zone of heated plasma found just inside the heliopause, apparently produced by the mixing of some interstellar plasma with the heliospheric plasma at the boundary. This layer was not thick, perhaps only a fraction of an astronomical unit, but its existence confirmed a key prediction of some theoretical models and provided the first direct evidence of plasma mixing at the heliopause. Understanding this mixing process is important for understanding how the heliosphere interacts with the interstellar medium over long timescales, and it has implications for the overall energy balance of the heliosphere. The crossing also allowed the team to test predictions about the heliopause's stability. Some models had predicted that the heliopause would be subject to Kelvin-Helmholtz instabilities, the same type of instability that forms waves on the surface of the ocean when wind blows across water, because the two plasmas on either side of the boundary are moving at different velocities relative to each other. If such instabilities were active at the time of the crossing, they would cause the heliopause to be rippled and irregular, with the spacecraft crossing the boundary multiple times in rapid succession as it passed through the undulating surface. Voyager 2's crossing was relatively clean and rapid, suggesting that at least in the region and at the time of the crossing, the heliopause was not strongly unstable. But this may reflect conditions specific to that region and time rather than the general character of the heliopause. A Voyager 2's heliopause crossing, which occurred in November 2018, more than 6 years after Voyager 1's crossing, provided a second independent measurement of the heliopause's magnetic field properties from a different direction. Since Voyager 2 had a functional plasma instrument, the measurement of the heliopause properties was considerably more complete than what had been possible with Voyager 1. The crossing was detected through changes in the plasma, particle, and magnetic field data occurring over approximately a day, a much more rapid transition than had been expected, suggesting a relatively thin heliopause rather than the broad transition zone some models had predicted. At the time of Voyager 2's heliopause crossing, the spacecraft was at approximately 119 astronomical units from the Sun, and it was heading in a direction roughly 37 degrees south of the ecliptic plane, very different from Voyager 1's roughly 35 degrees north trajectory. The difference in crossing distances, Voyager 1 at about 122 astronomical units, Voyager 2 at about 119 astronomical units, confirmed the asymmetry of the heliosphere. The upstream nose of the heliosphere, facing into the incoming interstellar medium flow, is compressed, while the downstream tail is elongated. Both spacecraft, heading in generally upwind directions, crossed the heliopause at broadly similar distances, though the small difference reflects the detailed geometry of the heliosphere. One of the most important results from Voyager 2's heliopause crossing was the measurement of a boundary layer, a thin region of heated plasma immediately inside the heliopause. This layer, which the spacecraft's plasma instrument detected as an abrupt increase in temperature just inside the boundary, suggests that the heliopause is not simply a contact discontinuity between the two plasmas, but an active region where the two plasmas interact, mix to some degree, and transfer energy. This boundary layer had been predicted by some theoretical models, but had never been directly confirmed before Voyager 2's measurements. The magnetic field measurements beyond the heliopause also confirmed something important. The interstellar magnetic field in the region immediately surrounding our solar system is stronger and more ordered than many pre-mission estimates had suggested. The field was well defined, persistent, and consistent over the years of data from Voyager 1, suggesting a relatively organized local interstellar magnetic environment rather than a highly turbulent one. This has implications for understanding how the interstellar medium is structured on the scale of light years surrounding the solar system. So what is interstellar space actually like now that two spacecraft have directly measured it? The answer is not what most people imagine when they think of the void between the stars. Interstellar space is not empty. It is not silent. It is not cold in the simple sense of containing no energy. It is a plasma, a partially ionized gas, with its own temperature, its own magnetic field, its own waves and oscillations. The region of interstellar space that Voyager 1 and Voyager 2 are currently traversing is part of what astronomers call the local interstellar cloud, also known as the local fluff, a warm, diffuse cloud of partially ionized gas approximately 30 light-years across that the solar system has been moving through for the past 44,000 to 150,000 years. Estimates vary. This cloud is itself embedded within a larger structure called the local bubble, a region of the Milky Way, roughly 1,000 light-years across, that was excavated by one or more supernova explosions over the past several million years, and is characterized by a hot, extremely tenuous plasma that is distinct from the denser interstellar medium found in other parts of the galaxy. The local interstellar cloud has a temperature of roughly 6,000 to 8,000 Kelvin, much warmer than one might naively expect for interstellar material, but still far cooler than the solar corona or the heliosheath. It has an electron density of approximately 0.04 to 0.1 electrons per cubic centimeter, consistent with what Voyager's plasma wave measurements have found just outside the heliopause. It contains hydrogen, both neutral hydrogen and ionized hydrogen, as well as helium, and trace amounts of heavier elements. The neutral hydrogen and helium in the local interstellar cloud flow into the heliosphere from one particular direction, a flow that has been detected and characterized by various spacecraft, and that represents a direct connection between the heliosphere's interior and the interstellar environment that surrounds it. The interstellar magnetic field in the local interstellar cloud is measured at roughly 2 to 3 microgauss, extraordinarily weak by any everyday standard, but significant for the dynamics of the interstellar medium and for the structure of the heliosphere. This field is oriented at a particular angle relative to the direction of the interstellar medium's flow relative to the solar system, and the geometry of that orientation influences the shape of the heliosphere in ways that are still being actively modeled and studied. It is important to appreciate just how strange and counterintuitive the interstellar medium is when considered from the perspective of human experience. We tend to imagine space as emptiness, the cold void between the stars, and in one sense it is. The density of the interstellar medium is so low that by any terrestrial standard, it is a far more perfect vacuum than anything we can achieve in a laboratory on Earth. A cubic centimeter of the best vacuum attainable in a laboratory might contain a few billion molecules. A cubic centimeter of the interstellar medium contains, at most, a few atoms or ions. It is, by any conventional measure, essentially nothing. And yet, it is not nothing. The interstellar medium has energy. It has magnetic fields, it has waves and turbulence. It has charged particles moving at close to the speed of light. It has photons from every star in the galaxy passing through it in all directions. It has neutral gas that, although astonishingly sparse, still exerts pressure and can be swept up by moving bodies, carrying momentum and affecting their trajectories over sufficiently long timescales. The interstellar medium is a medium in the full physical sense, a substance through which waves can propagate, through which energy can flow, through which a spacecraft passing through it can, in principle, be measured and characterized. What Voyager measures as it moves through the local interstellar medium is the cumulative effect of all these components. The plasma wave instrument registers the oscillations of the electron. The magnetometer registers the magnetic field. The cosmic ray instruments register the energetic particles. The low energy charged particle instrument registers the ions and electrons of more modest energies. Together, these measurements paint a picture of the local interstellar medium that is far richer and more detailed than any remote observation could provide. A picture that is fundamentally a picture of our galactic neighborhood as it exists right now, sampled directly and in situ for the first time in human history. The cosmic ray environment outside the heliopause, as measured by Voyager 1, is consistent with what would be expected for the local interstellar medium in the vicinity of the Sun. The flux of galactic cosmic rays at various energies matches predictions based on models of cosmic ray propagation through the galaxy, calibrated by measurements from other types of observations. This confirmation is important because it means that the Voyager measurements are probing genuine interstellar space, not some unusual or aberrant environment, and that the interstellar medium in our galactic neighborhood is reasonably well understood in broad outline. One of the most striking features of the interstellar medium, as measured by Voyager, is the absence of the anomalous cosmic rays that were abundant in the heliosheath. Anomalous cosmic rays are formed when neutral interstellar atoms drift into the heliosphere, become ionized either by solar ultraviolet radiation or by charge exchange, and are then picked up by the solar wind and eventually accelerated to high energies at the termination shock. This process is unique to the interior of the heliosphere. It requires the combination of neutral interstellar atoms, the solar wind, and the termination shock to produce the anomalous cosmic ray population. In interstellar space, beyond the heliopause, there is no termination shock, and there is no solar wind to create this population. The absence of anomalous cosmic rays outside the heliopause is therefore one of the clearest and most unambiguous confirmations that Voyager 1 and Voyager 2 have truly exited the heliosphere. Consider the arithmetic of Voyager's journey from a different angle. The solar system, as conventionally measured to Neptune's orbit, spans about 30 astronomical units, roughly 4.5 billion kilometers. The entire planetary system, the region we think of as the solar system in the colloquial sense, occupies a volume that Voyager 1 crossed in less than 12 years. The termination shock, the first boundary of the heliosphere beyond the planets, adds another 70 or so astronomical units, more than twice the distance from the Sun to Neptune. The heliosheath adds another 25 to 35 astronomical units, and the heliopause, where the solar system in the full physical sense finally ends, sits at approximately 120 astronomical units. From the Sun to the true edge of the solar system, the heliopause is a distance roughly 4 times the size of the planetary system that we tend to think of as comprising the solar system. Most of what the Voyager spacecraft crossed on their way to interstellar space was not the solar system that you might draw in a textbook. It was the vast, invisible, extended domain of the solar wind, a territory that has no planets, no moons, no asteroids, but that is nonetheless entirely shaped by the Sun's magnetic activity and outflow. This framing matters because it illuminates just how parochial our ordinary concept of the solar system is. When we say the solar system, we usually mean the system of planets orbiting the Sun. But the Sun's physical domain, the region of space that is physically dominated by the Sun's particles and magnetic field, is roughly 64 times larger in volume than the planetary system alone. The heliosphere is the solar system in its full physical extent, and the Voyager spacecraft spent most of their journeys traversing this vast outer domain that lies beyond the last planet but remains under the Sun's influence. It is worth pausing here to consider the scale of what we are talking about. The numbers involved in describing Voyager's journey are not merely large, they are large in a way that strains human intuition to its limits. As of 2024, Voyager 1 is approximately 23 billion kilometers from the Sun, more than 157 astronomical units. Voyager 2 is approximately 19 billion kilometers away, or about 130 astronomical units. These are the most distant human-made objects in existence. Nothing else made by human hands has ever gone as far. To travel from Earth to the Sun takes light approximately 8 minutes. To reach Voyager 1's position, light must travel for approximately 22 hours. A signal sent from Earth to Voyager 1 at the speed of light takes over 22 hours to arrive. The signal that Voyager 1 transmits back, carrying its scientific data and engineering telemetry, is emitted at a power of just 22 watts, roughly comparable to a dim light bulb. By the time it reaches Earth, spread across the vast distance, it has been attenuated to an almost incomprehensible degree. The signal power received by the Deep Space Network antennas on Earth is roughly 20 femtowatts, 20 millionths of a billionth of a watt. And yet, because the physics of radio transmission is well understood and the Deep Space Network antennas are extraordinarily sensitive, that signal can be received, decoded, and used to reconstruct the scientific data measured by Voyager's instruments. The spacecraft itself is operating on power provided by radioisotope thermoelectric generators, devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity. When Voyager 1 was launched, its RTGs produced approximately 470 watts of electrical power. Due to the natural decay of the plutonium and the gradual degradation of the thermoelectric converters, that power output has declined over the decades. By the mid-2020s, the available power is less than 40% of the original output. Mission controllers at JPL have had to carefully manage which instruments remain operational, turning off heaters and other non-essential systems to conserve power for the most scientifically valuable instruments. This power constraint is a ticking clock. As the power continues to decline, it will become necessary to shut down science instruments one by one to keep the most critical ones operating. Eventually, sometime in the late 2020s or early 2030s, the power will fall below the threshold needed to operate any science instrument, and Voyager will go silent. Not destroyed, not crashed, but simply running out of the energy needed to continue measuring and communicating. It will continue its journey through interstellar space in silence, carrying its golden record, its memories of the planets it visited, the data it has collected, and the achievements of the engineers and scientists who built it and operated it for half a century. At its current speed of approximately 17 kilometers per second, Voyager 1 is traveling outward at roughly 3.6 astronomical units per year. In 40,000 years, it will pass within approximately 1.6 light-years of the star Gliese 445, which is currently moving toward our solar system from the direction of the constellation Camelopardalis. This is not a particularly close stellar encounter. 1.6 light-years is still a vast distance, but it is a reminder that on cosmological timescales, the galaxy is a more connected place than it appears from our vantage point. Voyager 1 will wander through the interstellar medium for billions of years, barring an unlikely collision with another body or destruction by some unforeseen process. It will outlast the Sun, the solar system, and, perhaps, life on Earth. There is a broader scientific significance to the Voyager heliopause crossings that extends far beyond the specific measurements made in the outer heliosphere. What Voyager has done, for the first time, is allow scientists to directly measure the properties of the heliosphere as a whole system, not from the inside looking out, but by crossing the boundaries and comparing conditions on both sides. Before Voyager's heliopause crossings, the structure of the heliosphere was inferred largely from theory, from remote sensing observations, and from measurements made in the inner solar system. The termination shock, the heliosheath, and the heliopause were known to exist in broad outline. The theory of the solar wind and its interaction with the interstellar medium has been well developed since the 1950s and 1960s, with important contributions from Eugene Parker, Thomas Gold, Fred Hoyle, and many others. But the details, the thickness of the heliosheath, the structure of the heliopause, the transition in particle populations, the behavior of the magnetic field were genuinely unknown. Voyager's measurements have forced a significant revision of the models. The heliosheath is thicker than expected. The heliopause transition is sharper in some respects and more complex in others. The magnetic field behavior near the heliopause is more complicated than predicted. The stagnation region seen by Voyager 1 in the outer heliosheath was unexpected. The discovery of a hot boundary layer just inside the heliopause was unanticipated. In virtually every aspect of the detailed physics, the real heliosphere turned out to be more complex than the models. This is not a failure of the models. It is the normal and healthy process of science. The models captured the first-order physics correctly by explaining why the heliosphere exists and approximately where its major boundaries should be. The detailed measurements made by Voyager have provided the data needed to refine the models, to identify processes that had been neglected or incorrectly parameterized, and to develop a more accurate picture of the heliosphere's structure and dynamics. The heliosphere also has implications for understanding other stellar astrospheres, the analogous structures that exist around other stars, and every star with a stellar wind will produce an astrosphere, a region of space dominated by that star's outflow. For stars with weaker winds, the astrosphere may be smaller. For stars with stronger winds, it may be larger. The structure of the astrosphere depends on the properties of the stellar wind, the local interstellar medium, and the interstellar magnetic field in the vicinity of the star. The insights gained from Voyager's exploration of our own heliosphere are directly applicable to the interpretation of observations of other astrospheres. Radio observations, energetic neutral atom imaging, and other remote sensing techniques have been used to study the heliospheres of other stars, and the calibration provided by Voyager's in situ measurements is invaluable for interpreting these observations correctly. The heliosphere also plays a critical role in the habitability of the Earth. The shielding provided by the heliosphere against galactic cosmic rays is not merely of academic interest. Cosmic rays are a source of ionizing radiation that can affect biological systems, chemistry in the atmosphere, and the production of certain isotopes in the Earth's surface and atmosphere that are used to date geological and archaeological samples. Changes in the heliosphere's shielding effectiveness, driven by changes in the Sun's magnetic activity cycle and the long-term evolution of the Sun, may have influenced the biological evolution of life on Earth over geological timescales. The Voyager measurements, by quantifying the shielding effectiveness of the heliosphere, have contributed to understanding this aspect of Earth's long-term environment. It is perhaps one of the most extraordinary facts in the history of science that a spacecraft launched in 1977, designed and built with the technology of that era, is still functioning nearly 5 decades later and still making scientifically significant measurements from the edge of the solar system and beyond. The engineers who designed Voyager could not have anticipated that it would survive long enough to cross the heliopause. The original mission design was focused on the planetary encounters. The primary science objectives were completed within the first 12 years. With Neptune's encounter in 1989, everything after that has been a bonus. The longevity of the Voyager spacecraft is a testament to the engineering philosophy of the era: conservatism, redundancy, and careful design. The spacecraft were built with backup systems for virtually every critical function. The instruments were designed to be reconfigurable and operable in modes that were not anticipated at the time of construction. The Deep Space Network has been continuously improved over the decades to maintain the ability to communicate with spacecraft at ever greater distances. But it is also worth acknowledging the human dimension of this achievement. The scientists and engineers who have worked on the Voyager mission span multiple generations. Many of those who built the spacecraft and conducted the first planetary encounter, science, are no longer alive. The current team working with the Voyager data includes people who were not yet born when the spacecraft were launched. The mission has become an institution, a living thread of scientific inquiry that connects the early days of the space age to the present. The Deep Space Network, the global system of large radio antenna facilities used to communicate with spacecraft throughout the solar system and beyond, has invested enormous resources in maintaining the ability to communicate with Voyager. As the signal strength has declined with increasing distance, larger antennas and more sensitive receivers have been deployed. Software improvements have been made to the data processing systems. The intellectual and engineering infrastructure supporting Voyager's continued operation represents a continuous commitment by NASA and JPL to the principle that these spacecraft, ancient by the standards of modern technology, are still doing science that cannot be replicated any other way. No other spacecraft has crossed the Heliopause. The interstellar medium near the Heliopause has been directly sampled only by these two probes. There are no other missions currently en route to the boundaries of the heliosphere. The next spacecraft that could potentially follow in Voyager's path would take decades to arrive, and no such mission has been formally approved and funded as of the mid-2020s. Voyager 1 and Voyager 2 are therefore, for the foreseeable future, humanity's only direct ambassadors to interstellar space. But no matter how advanced a future interstellar probe might be, it will owe its scientific foundations to Voyager. Voyager defined the questions. Voyager identified the boundaries. Voyager showed us, in precise quantitative detail, what happens when the Sun's kingdom ends and the interstellar realm begins. A future mission will refine and extend what Voyager discovered. It will not diminish it. There is something almost poignant about the conversation between the Voyager team and the spacecraft. A signal takes 22 hours to reach Voyager 1 at its current distance. Any command sent to the spacecraft, any instruction to adjust an instrument, to change a telemetry mode, to fire a thruster, requires a round-trip communication time of nearly 2 days. This means that Voyager operates with a significant degree of autonomy. When unexpected conditions arise, the onboard systems must respond without waiting for instructions from Earth. The engineers who programmed Voyager's fault protection systems in the 1970s wrote code designed to handle problems that they could not entirely anticipate, a remarkable exercise in engineering foresight. In 2023, Voyager 1 experienced a technical anomaly that illustrates both the fragility and the extraordinary resilience of the spacecraft. The flight data system, one of the computers responsible for packaging science and engineering data for transmission to Earth, began returning garbled telemetry, repeating a pattern of ones and zeros rather than transmitting intelligible data. The mission team spent months analyzing the problem from more than 23 billion kilometers away, with each diagnostic command taking 22 hours to reach the spacecraft and another 22 hours to receive the response. Eventually, they determined that a single chip in the flight data system memory had failed, corrupting the code stored in that location. By developing a creative solution, distributing the affected code across different parts of the memory, and carefully rewriting the software to work around the bad chip, the team restored normal data transmission. This fix was itself an extraordinary feat of remote engineering. Performed on a 46-year-old computer operating in interstellar space with a communication round trip of nearly 2 days. The fact that this repair was possible at all speaks to the quality of the original engineering documentation. The team still had detailed technical drawings and code listings from the 1970s, carefully preserved through the decades, that allowed them to understand the internal architecture of a system designed before most of the current engineers were born. It also speaks to the depth of institutional knowledge at JPL, where a small team has maintained continuous expertise in Voyager's systems across multiple generations of engineers. This episode is a reminder of what is at stake as the spacecraft age. There will be more anomalies. Some will be repairable, others may not be. The clock is running not just on the power, but on the spacecraft's mechanical and electronic systems, on the expertise of the people who maintain them, and on the institutional memory that makes complex remote repairs possible. There have been discussions for decades about future missions to the Heliopause and beyond, what some researchers call an interstellar probe mission. Conceptual designs for such a mission have been developed by scientists at Johns Hopkins University Applied Physics Laboratory and elsewhere, and the idea received a significant endorsement in the 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, which listed an interstellar probe mission among its high-priority large mission recommendations. The concept envisions a spacecraft launched with a much higher initial velocity than the Voyagers, using either a large heavy-lift rocket with a solar gravity assist maneuver, flying very close to the Sun to gain enormous speed, or some form of advanced propulsion. The goal would be to reach the Heliopause region within 15 to 25 years, rather than the 35 years it took Voyager, and to carry a suite of modern instruments far more capable than those on Voyager, including instruments capable of directly sampling interstellar plasma and magnetic fields with much higher time and energy resolution, cameras capable of imaging the heliosphere from the outside for the first time, and instruments capable of studying the properties of interstellar dust. An interstellar probe would answer many of the questions that Voyager has raised. It would map the full three-dimensional structure of the heliosphere. It would cross the heliopause in a controlled, scientifically optimized trajectory, rather than along the paths that the Voyagers happened to follow. It would sample the interstellar medium at multiple distances beyond the heliopause, allowing the density and magnetic field profiles to be characterized. It would operate for perhaps 50 years, reaching distances of 300, 400 astronomical units from the Sun, well into the interstellar medium, and perhaps approaching the inner boundary of the Oort cloud. But no matter how advanced a future interstellar probe might be, it will owe its scientific foundations to Voyager. Voyager defined the questions. Voyager identified the boundaries. Voyager showed us, in precise quantitative detail, what happens when the Sun's kingdom ends and the interstellar realm begins. A future mission will refine and extend what Voyager discovered. It will not diminish it. We should also address the sheer strangeness of what has been revealed about the boundary of our solar system, the ways in which the edge of the heliosphere is unlike anything in the inner solar system, or in simple theoretical models. One of the most striking revelations concerns the fundamental geometry of the heliosphere itself. For decades before Voyager's boundary crossings, the dominant theoretical picture of the heliosphere was what physicists call the blunt nose model. The heliosphere was thought to be shaped roughly like a comet, with a rounded, compressed front end facing into the incoming interstellar flow, and a long, tapering tail stretching behind it in the downstream direction. This model was elegant, well motivated by the physics of supersonic flows interacting with stationary obstacles, and broadly supported by indirect evidence. But the picture has grown more complex. Data from the IBEX spacecraft, the Interstellar Boundary Explorer, a NASA mission launched in 2008, specifically to study the heliosphere from the inside using energetic neutral atom imaging, revealed that the heliosphere may not have a long, comet-like tail at all. The data suggested instead a structure more like a croissant, with two lobes deflected to either side by the interstellar magnetic field, and a much shorter, less well-defined downstream region than the classical picture implied. This result remains controversial, with different research groups interpreting the data differently, but it illustrates the degree to which even the gross shape of the heliosphere is still an active area of scientific debate. What is not in debate is that the Voyager boundary crossings provided ground truth measurements, direct, in situ characterizations of the termination, shock, heliosheath, and heliopause, that no model can contradict. The models can be adjusted and refined to match Voyager's observations, and indeed, this process of model adjustment has been ongoing since the termination shock crossings in the mid-2000s. Each unexpected observation, the stagnation region in the outer Helios Heath, the thin Heliopause transition measured by Voyager 2, the persistent magnetic field direction similarity across the Heliopause measured by Voyager 1, has prompted revisions in the theoretical picture. The models that exist today are substantially more sophisticated and more accurate than those that existed before the Voyager boundary crossings, and they are more accurate precisely because they have been forced to account for the unexpected details that Voyager revealed. The termination shock, for instance, turned out to be not a single, clean boundary, but a fluctuating, rippling structure that moved back and forth across the Voyager spacecraft's position multiple times during the crossing. The shock moved inward and outward by several astronomical units in response to changes in the solar wind, which was itself responding to the 11-year cycle of solar magnetic activity and to individual solar events. This meant that the termination shock crossing was not a single event, but a series of episodes, an extended encounter with a dynamic boundary. The heliosheath, once entered, revealed that the solar wind does not simply decelerate and flow outward smoothly. It meanders, it stagnates, it is subject to turbulence on a grand scale. The magnetic field in the heliosheath was observed to be dominated by large-scale structures, sectors where the field pointed predominantly in one direction, alternating with sectors where it pointed in the opposite direction, a pattern inherited from the Sun's own magnetic field, polarity reversals during the solar cycle. These sector boundaries, called heliospheric current sheets in the inner solar system, persist out to the heliopause and influence the particle populations and dynamics of the heliosheath. The heliopause itself was found to be a surprisingly sharp boundary in some respects. The change in particle populations occurred over a distance of only a few tenths of an astronomical unit in the case of Voyager 2's crossing, yet it is simultaneously a leaky boundary with some mixing of solar and interstellar particles in the transition region. The boundary layer of heated plasma detected just inside the heliopause by Voyager 2 suggests active energy exchange between the solar and interstellar plasmas in the transition region. And beyond the heliopause, the interstellar medium itself is not the simple uniform medium that some early models assumed. The plasma wave oscillations detected by Voyager 1 have revealed density variations in the interstellar medium. The magnetic field strength and direction have shown variations. The cosmic ray flux, while broadly consistent with the local interstellar medium predictions, shows fluctuations that are still being characterized. The nearby interstellar medium is a dynamic, structured environment, not a static void. All of this complexity, the rippling termination shock, the turbulent heliosheath, the layered heliopause, the structured interstellar medium, reflects the fact that the boundary between the solar system and the galaxy is not a wall, but a conversation. The Sun's wind and magnetic field interact continuously with the interstellar medium. Neutral atoms drift inward from the interstellar medium, penetrating deep into the heliosphere before being ionized and picked up by the solar wind. Energetic particles diffuse outward from the termination shock into the heliosheath and across the heliopause into the interstellar medium. Pressure waves from solar eruptions propagate outward and disturb the local interstellar plasma. The boundary breathes, it flexes. It is alive in the sense that it is continuously shaped by the Sun's changing activity and by the properties of the medium surrounding it. This is one of the most profound lessons of the Voyager mission, that the solar system does not end at a wall. It fades, it transitions, it converses with the rest of the galaxy through exchanges of particles, energy, and magnetic field that span the entire breadth of the heliosphere. The boundary is real. The particle populations on either side are fundamentally different. The plasma properties are distinct. The magnetic field structure changes, but it is not simple, not rigid, and not passive. As we reach the closing of this story, it is worth returning to the beginning, to the fact that what we are describing is not a computer model or a theoretical prediction, or an indirect inference. It is the record of a machine that humanity actually built and actually launched, and that actually went there. There is a question that comes up when one contemplates the Voyager mission deeply enough. What does it mean to have done this? Not in the practical scientific sense, the measurements, the discoveries, the model refinements, but in the larger, more philosophical sense. We live on a planet orbiting a star. That star has a domain, a region of space it fills with its wind and its magnetic field and its energy. This domain is the heliosphere, and for billions of years it has existed without any inhabitant of that domain knowing it was there. The Earth circled the sun. Life evolved. Civilizations rose and fell, and all the while, the solar wind was blowing outward. The heliosphere was expanding and contracting with the solar cycle. The heliopause was fluctuating in response to the interstellar medium, and galactic cosmic rays were streaming in from supernova remnants tens of thousands of light years away, partially shielded by the sun's magnetic influence. None of this was observed. None of it was measured. It simply was. And then, in the second half of the 20th century, something changed. A civilization on that orbiting planet developed the capacity to understand enough physics to calculate where the boundaries of its star's domain lay. It built machines capable of surviving the journey to those boundaries. It launched 2 of those machines with enough energy to escape the sun's gravitational pull and enough power to transmit data for decades. And those machines found the boundaries and crossed them and told their creators what was there. This is not merely a technological achievement. It is an epistemological transformation. The heliosphere, which had been known only indirectly and theoretically, became known directly and empirically. The interstellar medium, which had been characterized only through remote observation, through the absorption spectra of starlight, through the scattering of radio waves, through the diffusion of cosmic rays, was sampled in situ for the first time. The edge of our solar system, which had been a theoretical construct, became a measured reality. The Voyager spacecraft carry with them a kind of dual testimony. On one level, they are scientific instruments, exquisitely designed to measure the physical properties of the environments through which they pass. On another level, they are monuments, artifacts of a civilization that, in the late 20th century, had the knowledge to understand the structure of the solar system, the technical capability to build spacecraft that could survive for half a century in space, and the vision to send those spacecraft not just to the outer planets, but through the boundary of the heliosphere and into the space between the stars. The golden records aboard each spacecraft are perhaps the most frequently discussed aspect of this testimony. Carl Sagan, who was instrumental in designing them, described them as a message in a bottle thrown into the cosmic ocean. They carry sounds and images selected to represent the diversity of life and culture on Earth. The sound of rain and surf and thunder, the songs of whales and birds, music from dozens of traditions, spoken greetings in 55 languages, images of landscapes and scientific diagrams, and human beings engaged in the activities of life. Whether any intelligence will ever encounter these records and comprehend their contents is, in the most literal sense, unknowable. But that is not quite the point. The records are as much a statement about what kind of species sent them as they are a message to any hypothetical recipient. A species that could make and launch Voyager, that could navigate it through the outer solar system and track it to the edge of interstellar space and beyond, and that would choose to include on it not just technical information, but music and human voices and the sound of a mother's first words to her child. This is a species that has not merely survived on its planet, but has reached out beyond it, carrying something of its soul into the galaxy. Voyager 1 is currently in the interstellar medium, truly, by any rigorous physical definition, outside the solar system. It is surrounded not by solar plasma, but by the interstellar medium of the Milky Way. The closest star to the solar system, Proxima Centauri, is approximately 4.24 light-years away. At Voyager 1's current speed, it would take approximately 73,000 years to travel that distance. And Voyager 1 is not heading toward Proxima Centauri. The interstellar distances are not going to be bridged by Voyager or by any spacecraft we could build today. But that is not, perhaps, the relevant measure of what has been achieved. The relevant measure is this: For the first time in the history of life on Earth, a human-made object has left the domain of the Sun. It has crossed the Heliopause. It has entered the space between the stars. It is measuring the properties of the local interstellar medium, the very material out of which the Sun and its planets were condensed 4.5 billion years ago, the medium through which the solar system is moving as it orbits the center of the galaxy, the environment that shaped the boundary conditions of our heliospheric home. There is a further dimension to this that deserves reflection. The interstellar medium that Voyager is now moving through is ancient. The atoms of hydrogen and helium in the local interstellar cloud are remnants of the Big Bang, forged in the first minutes of the universe's existence. The heavier elements mixed into this medium, the carbon, the oxygen, the silicon, and the iron, were produced in the cores of stars that lived and died before the Sun was born, scattered into the interstellar medium by supernova explosions, and eventually incorporated into the molecular cloud that collapsed to form our solar system 4.5 billion years ago. The interstellar medium is, in a profound sense, the source material of everything in the solar system, including the atoms in our own bodies. Voyager is sampling the substance from which we were made. The cosmic rays that Voyager's instruments are now counting as they stream through the spacecraft's detectors are particles that were accelerated in supernova remnants hundreds or thousands of light years away, perhaps millions of years ago. They have been traveling through the galaxy at close to the speed of light, bouncing along magnetic field lines, slowly diffusing through the interstellar medium, and now, one by one, they are being registered by a small electronic detector on a spacecraft launched from a planet orbiting a modest star in one of the Milky Way's spiral arms. There is something remarkable about this chain of events, from a stellar explosion to a detector built by human hands to a data record transmitted back to Earth and analyzed by scientists who understand what they are looking at. Voyager's journey is not an isolated technological achievement. It is a chapter in the much longer story of how a species that evolved on a single rocky planet came to understand the universe it inhabits, from the structure of atoms to the large-scale distribution of galaxies, from the nuclear reactions that power the Sun to the cosmic ray particle acceleration in distant supernova remnants, from the geochemistry of planetary surfaces to the plasma physics of interstellar boundaries. Voyager's instruments, measuring the plasma wave oscillations and the cosmic ray fluxes and the magnetic field orientations at the edge of the solar system, were contributing data to this story, a story that has no foreseeable end. The signals are still coming. 22 hours of travel time for a radio wave moving at the speed of light, a 22-watt transmission from a spacecraft 23 billion kilometers away, received as 20 femtowatts at the surface of the Earth, engineering telemetry and scientific data encoded in that vanishingly faint signal, decoded by the Deep Space Network, and transmitted to the scientists who spend their working lives trying to understand what it means. In the outer interstellar medium, Voyager 1 is falling into silence. Its power is failing. Its instruments are being turned off one by one, conserved like the last few drops of water in a canteen. Within a few years, perhaps a decade at most, the last instrument will have to be switched off, and Voyager will continue outward in the dark, with no power to transmit, no instruments to measure, no signal to send, but still moving, still carrying the golden record, still a part of the story of life on Earth, and the universe through which it drifts will have no opinion about it whatsoever. The interstellar medium will part around it with perfect indifference. The cosmic rays will pass through it without noticing. The magnetic field will barely deflect around its metallic body. The stars that lie ahead on its trajectory, Gliese 445, and then tens of thousands of years later, other stars, and then billions of years later, the eventual transformation of the galaxy itself, will not care. But we care. We built this machine. We launched it. We tracked it across 23 billion kilometers and decoded the whisper of its transmissions and translated that whisper into an understanding of where the solar system ends and the galaxy begins. We are the species that did this with 47-year-old technology, with 1970s computers and 1970s engineering and 1970s rocket fuel. Perhaps the most important thing that Voyager has taught us is not any of the specific measurements it has made, not the electron density of the local interstellar medium, not the thickness of the heliosheath, not the behavior of the magnetic field at the heliopause. The most important thing it has taught us is the size of the place we live in. The solar system is not merely the system of planets that we draw in textbooks. It is a vast bubble of solar influence, roughly 240 astronomical units across at the nose, that moves through the galaxy surrounded by an ancient and complex interstellar medium. We live inside this bubble, the sun maintains it, and we have now crossed its boundaries and touched what lies beyond. That is not a small thing. That may, in fact, be among the largest things our civilization has yet done. The edge of the solar system is not empty. It is not featureless. It hisses with plasma waves. It crackles with cosmic radiation. It marks the place where the sun's long reach finally, after 4.5 billion years, runs out. And we know this not because we imagined it or calculated it, but because we sent something there, something with instruments and power and a radio transmitter and a golden record of our voices. And it told us what it found 47 years into its journey, still transmitting, still measuring, still reaching back across the dark